We have already discussed the working principle of Mamdani approach or fuzzy reasoning tool in the form of fuzzy logic controller. Now, today we are going to discuss one numerical example, like how to solve a numerical example using the Mamdani approach. Now, the statement of the problem is as follows. Now, let us suppose a problem scenario related to navigation of a mobile robot in the presence of 4 moving obstacles. Now, here we are going to solve one navigation problem of mobile robots, and this particular problem is known as actually the dynamic motion planning problem. So, this is the dynamic motion planning problem, and this is nothing but a navigation problem of a mobile robot in the presence of some moving obstacles. Now, here I am just going to explain the problem scenario. Now, for simplicity, the robot, the physical robot has been represented by a point. So, this is nothing but the point robot, and the starting position of the point robot is denoted by S. And supposing that the goal of this robot is indicated by the point G. So, G is the goal and S is the starting point. Now, let us consider one hypothetical situation that there is no such moving obstacles here. Now, if there is no such moving obstacle and this is the starting point and this is the goal, and if I say to find out one collision free time optimal path, the robot will try to find out. So, this particular path, and this is actually the optimal path if there is no such moving obstacles in the workspace. But here the physical problem is slightly different in the sense we have got a few moving obstacles. For example, say we have got obstacle 1, that is denoted by O 1, then comes we have got obstacle O 2, then we have got obstacle O 3 and obstacle O 4. Now, what is our aim? Our aim is to find out the collision free and time optimal path for this particular robot starting from point S to reach that point G. Now, to solve this particular problem, the first thing we will have to do is you will have to find out the most critical obstacle for the robot. Now, this is actually the direction of the speed. So, this is the velocity direction for the different obstacles. Now, here to determine the critical obstacle, like your most critical obstacle. So, what I will have to do is I will have to see at least your two things. One is the distance between the present position of the robot and that of the obstacle, and another is the direction of movement. Now, here if you see the obstacle O 1 is moving in this particular direction, obstacle O 2 is moving in this particular direction, O 3 is in this direction and O 4 is in this particular direction. Now, if I consider both the distance as well as the moving direction, so very easily we can find out the most critical obstacle is nothing but is your O 2. So, O 2 is the most critical obstacle. That means, to avoid collision with the most critical obstacle, so I will have to make some planning with the help of your fuzzy reasoning tool. So, I am just going to develop one fuzzy logic controller or the fuzzy reasoning tool, so that the robot can avoid collision with this particular the most critical obstacle. Now, to solve this particular problem, actually what we do is we take the help of one fuzzy reasoning tool or fuzzy logic controller. So, let me write here FLC, and for this FLC there should be a few inputs and output also. Now, what we do is the distance between the robot and the most critical obstacle, and it's we will have to consider its boundary. So, this particular distance is nothing but one input for the fuzzy reasoning tool, and another input could be the included angle, that is your G, S and O2. So, this particular angle could be another input. So, let me write here angle is another input, so denoted by A, and we will have to find out one output of the fuzzy reasoning tool. That output could be the angle of deviation to avoid the collision with the most critical obstacle. Now, supposing that the angle of deviation to avoid the collision, it could be something like this. So, this could be the direction of movement of the robot just to avoid collision with the most critical obstacle. Now, if this is the scenario, so this particular angle, that means your, if I just give one point here, say D. So, the angle GSD is nothing but is actually the deviation. Now, this deviation, so I can write down that is by say D prime. So, D prime is nothing but the angle of deviation to avoid collision with this particular the most critical obstacle. Now, let us see how to solve this particular problem using the principle of the Mamdani approach of fuzzy reasoning tool. Now, here the membership function distribution for this distance and the input angle. So, we have considered something like this, and this is nothing but the membership function distribution for the output, that is your the deviation. Now, if you see, if you concentrate on the database or the membership function distribution for the distance. So, the range for the distance has been considered as 0.1 to 2.2 meter, and the whole range that is actually distributed or that is represented using 4 linguistic terms. For example, we have got very near, then comes near, far and very far, and for simplicity the membership function distribution has been considered to be triangle. Now, I could have considered some sort of nonlinear distribution also like Gaussian, but here for simplicity we have considered the triangular membership function distribution, and you can see that there is a overlapping. For example, this near distance and far distance, there will be some sort of overlapping, and that is actually according to the definition of the fuzzy sets. Now, the angle input that is divided into the range is divided into 4 or 5 linguistic terms. For example, say, so if the angle is between minus 45 to 45, minus means say if I consider this is clockwise, and plus if I consider it is anti-clockwise. So, minus 45 to plus 45, that means if I consider my left hand side is negative and my right hand side is positive, that is also possible. So, this A stands for the ahead, the angle is ahead. So, this angle ahead that is defined in the range of minus 45 degree to plus 45 degree. Similarly, we have got ahead right ART, and that is defined in the range of 0 to 90 degree. Then we have got right, that is RT plus 45 to 90. Then we have got ahead left, so from minus 90 to 0, and then comes your left, that is denoted by LT. So, minus 90 to minus 45. So, there are 5 such linguistic terms to represent the angle input. Now, similarly, to represent the deviation, that is the output of the fuzzy logic controller, once again we are using 5 linguistic terms like your ahead, ahead right, right, then comes ahead left and left. So, this is the way actually we will have to manually design the database, that is the membership function distribution for the 2 inputs and 1 output. And once you have got this particular the membership function distribution, now we are in a position to design this particular the rule base, that is the manually constructed rule base. That means, the based on the information of this particular problem of the designer. So, designer is going to design this particular the rule base. Now, we have seen that for the distance input we have got like 4 linguistic terms, and for the angle input we have got 5 linguistic terms. So, we have got 4 multiplied by 5, like 20 possible combinations of the input variables, and we have got a maximum of 20 rules. Now, this actually table shows all such 20 rules. Now, here I have put distance, and distance is expressed in terms of the linguistic terms like very near, near, far and very far. And this particular angle input is represented, as I told, left, ahead right and right. Now, the first entry, that is your first row first column entry, it indicates A. A means your ahead. So, this is nothing but the deviation. So, corresponding to this particular entry, so if I write down the rules, it looks like this. So, if the distance d is very near and the angle is the left, then the output, that is nothing but the deviation, that is d prime. So, this is nothing but, so d prime is nothing but is your ahead. So, this is nothing but this is nothing but a rule. Similarly, we have got 20 such rules here. Now, this particular rule base has to be manually designed, but it may not be the optimal one, and we will be discussing one method how to optimize this particular rule base after some time. Now, here in this numerical example, the statement is not yet complete. Now, here what we will have to do is, so we will have to find out the output, that is the deviation for the set of inputs like distance is 1.04 meter and angle like GSO2 is nothing but 30 degrees, and we will have to use Mamdani approach, and we are going to use the different methods of defuzzification. Now, let us see how to proceed with this particular numerical example and how to solve it. Now, before I just go for that, so let me once again try to concentrate here. So, the distance is 1.04, that means I might be here. So, let me just draw here. So, this is my 1.04 distance, say it is 1.04 meter, and the angle input it was 30. So, might be I am here. So, if I am here, now corresponding to this particular 1.04, so this particular distance can be called near with this much of membership function value, and this can also be called far with this much of membership function value. Now, similarly, this angle 30 degree can be called this ahead with this much of membership function value, and it can also be called ahead right with this much of membership function value. Now, that means, if we just write it down here, so corresponding to this, so this is nothing but is your mu n r, and this is nothing but is your mu f r, and here, so this is nothing but is your mu ahead, and this is your mu ahead right. So, this is the way actually we can find out the membership function distribution for the set of inputs. Now, with this particular information, let me start with the finding the solution. Now, as I told that the distance of say 1.04 meter can be called either near or far. Similarly, the angle of 30 degree may be called either ahead or ahead right. Now, let us try to find out the membership function value. Now, how to determine the membership function value? It is very simple. Now, let me first concentrate on the distance is near. So, if you see the membership function distribution for the near distance, so I will be getting this type of distribution for the near in the range of 0.8 to 1.5, and here the input is your 1.04. Now, corresponding to 1.04, so my aim is to find out what should be this particular the mu. So, this mu actually I will have to find out. Now, what we do is we use the principle of similar triangle. Now, if I consider say this is one triangle and another triangle, if I consider something like this, if I consider another triangle is something like this. So, this is another triangle. So, these two triangles are actually similar. Now, if these two triangles are similar, then we can say that this angle is actually common to both the triangle, then your this particular angle is equal to that particular angle. So, I can use the principle of similar triangle. So, similar triangle if I use, then very easily can find out what should be the mu value. Now, here I have written, so x divided by your 1.0. So, x divided by 1.0 and opposite to that is this particular angle, and that is actually the common for both the triangles. Then you concentrate on this particular angle and that particular angle, they are also equal. So, now opposite to this is nothing but 1.5 minus 0.4. So, 1.5 minus 1.04, and opposite to this is nothing but 1.5 minus 0.8. So, 1.5 minus 0.8, and if you solve it, you will be getting x equals to 0.6571. So, this is the way by using the principle of similar triangle. So, very easily I can find out what should be the value of this particular x, and that is nothing but your mu n r. So, this is nothing but is your mu n r. Okay. So, mu n r is nothing but 0.6571. Now, once you have got this particular your the mu n r, so very easily you can find out what is mu f r. Now, this mu f r is nothing but is your 1 minus. So, this is the triangular membership function distribution, and this should be 1 minus 0.6571, and that is nothing but is your 0.3429. So, this 0.3429 is nothing but is your mu f r. Now, by following the similar procedure for the angle input of 30 degree can be called either ahead or ahead right. So, this can be called ahead with the membership function value of 0.3333, and this can also be called ahead right with the membership function value 0.6667. And once you have got these membership function values, now we are in a position just to find out what should be the fired rules. Now, here we have seen that the distance input could be either near or it could be far. Similarly, the angle input, it could be either the ahead or we have got ahead right. Now, using this particular information, so I can write down the 4 fired rule. There could be a maximum of 4 fired rules, because here we have got 2 possibilities for the distance and we have got 2 possibilities for the angle. So, 2 multiplied by 2, there could be a maximum of 4 fired rules. But what is the total number of rules we have in the rule base? That is nothing but 20. Then out of 20, a maximum of 4 can be fired. Now, what are the fired rules? If distance is near, the first fired rule is if distance is near, and now as I have already mentioned that this particular and is actually and operator, not the conjunction and that is why you have to write in capital. And angle A is A, then deviation is right. So, this is actually the first fired rule. So, I am using NR and A combination. Now, I will have to use NR and ART combination. That means, if distance is NR and angle is ART, then deviation is ahead. So, this is nothing but the second fired rule. Then comes your the third fired rule. So, I will have to use this particular FR along with A. So, if distance is far, that is FR, and angle is A, that is ahead, then deviation is ahead right. So, this is the third fired rule. Then comes the fourth fired rule. If distance is FR and angle is ART, then the deviation is A. So, as I mentioned, there could be a maximum of 4 fired rules, and out of these the maximum of 20 rules. So, these 4 fired the rules could be fired. Now, let us see how to determine the output corresponding to like each of the fired rules. Now, to determine the output of each of the fired rules, the first thing we will have to do is you will have to find out the firing strength of each of the fired rules. Now, the firing strength for the first rule, that is denoted by is your alpha 1, is nothing but the minimum between mu n r and mu a. Now, minimum between 0.6571, that is your mu n r, and mu a is nothing but 0.3333, and we will have to find out the minimum. So, this is nothing but the minimum. Similarly, the firing strength for the second rule, that is alpha 2, is the minimum between mu n r and mu a r t, and that is nothing but the minimum between 0.6571 and 0.6667, and the minimum is your 0.6571. Then comes your the third fired rule, and its firing strength, that is alpha 3, is nothing but the minimum between mu f r and mu a, that is the minimum between 0.3429 and 0.3333, and the minimum is your this. Now, we will have to concentrate on the firing strength of the fourth rule, that is your alpha 4, and that is nothing but the minimum between mu f r and mu a r t, and that is nothing but the minimum between 0.3429 and 0.6667, and actually the answer is 0.3429. So, this is the way actually we can determine the firing strength of each of these particular the rule. And once you have got the firing strength, now we are in a position to determine what should be the fuzzy-fired output corresponding to actually each of the fired rule. Now, here if you see the first fired rule, that is represented by actually this. So, this is nothing but the first fired rule, and if you see this particular rule, if distance is near and angle is ahead, then the deviation is right. So, this is actually the first fired rule, and what are the inputs? The inputs are distance is your 1.04 meter and the angle is your the 30 degree. So, these two inputs we are passing, and corresponding to the distance equals to 1.04. So, I will be getting actually 1 mu, and this is nothing but is your mu f r. So, this is your the mu n r. So, this is your mu n r, and similarly corresponding to the angle of 30 degree. So, I will be getting 1 mu here. So, this particular mu, and this mu is nothing but is your mu a. Now, we will compare. So, mu n r and your mu a, and there is an AND operator, there is a minimum operator. So, we will try to find out the minimum between this mu n r and mu a, and if you see the minimum is nothing but your mu a. So, I will be getting actually the output of the first fired rule is something like this. So, this is actually this shaded area is actually the output corresponding to the first fired rule. Now, by following the similar procedure, so I can also find out your what should be the output corresponding to the second fired rule. So, this is the second filed rule, and here corresponding to distance equals to 1.04. So, I will be getting mu n r is nothing but this. So, this is your mu n r, and corresponding to this particular angle. So, I can also find out the mu, and that is nothing but is your mu a r t. And if I just compare, so these two mu values, so minimum will be your mu n r, and corresponding to that actually I can find out what could be the fuzzified output. So, this is nothing but the fuzzified output, and truly speaking this is actually the membership function distribution for the ahead direction. Okay. So, this shaded portion is nothing but the fuzzified output corresponding to the second filed rule. Now, by following the similar procedure, so I can also find out what should be the fuzzified output corresponding to your the third filed rule. So, if I just concentrate on the third filed rule, so this is the third filed rule, and corresponding to the distance, so this is 1 mu. So, I will be getting 1 mu that, and I will be getting another mu here corresponding to the second input, and if I just compare these two mu, so this is the minimum. So, I will be getting the fuzzified output is nothing but, so this shaded area. Now, corresponding to your the fourth filed rule. Now, corresponding to the fourth filed rule, so what you can do is, so we can find out what should be the fuzzified output. Now, here corresponding to the distance input, so this is nothing but your mu, and here corresponding to the angle, so this is nothing but is your mu, and if I compare these two mu, so this is the minimum. So, the fuzzified output corresponding to your the fourth filed rule, so this will be something like this. So, this is the way actually we can find out what should be the fuzzified output for each of the filed rule, and after that actually we will have to use the OR operator just to combine actually all such outputs into one, and as I told, this OR operator is the max operator. So, we will have to superimpose all such the fuzzified output, the truncated area whatever we have got, and then we will have to use this OR operator or the max operator. So, just to find out what should be the fuzzified output considering all four filed rules. Now, if you see this particular the fuzzified output corresponding to your considering all the filed rules, now we will be getting actually this type of area. Now, if you just see, so corresponding to one of the filed rules, so you will be getting so this type of, you will be getting this type of your output. So, this output is corresponding to your one filed rules. So, this is the output. Now, corresponding to another rule, your the output was something like this. So, this is corresponding to another rule, and then comes your corresponding to another filed rule. So, the output is something like this. So, this is actually another fuzzified output. So, this is the fuzzified output, and corresponding to your say another corresponding to your, so another you can find out. So, this is nothing but is your the fuzzified output. So, all such things actually now you will have to superimpose to find out what should be the fuzzified output considering all the filed rules. Now, these are all fuzzified output, that means this is actually the fuzzified output, now which cannot be directly used for controlling a particular process or to take any decision. So, what you will have to do is, so from this fuzzified output actually you will have to find out the crisp output. So, how to find out the crisp output, that I will be discussing. Thank you.